Okay, this last video on Equilibria and KC, we are looking at how KC and numbers are used together in exam questions. So here is an interesting little problem. Here you've got two separate temperatures at which the reactions A and B were done at. Okay, so these are two separate reactions. So reaction A, the numerical value for Kc is 5000. At 800 Kelvin, the numerical value for Kc is 0.3. In reaction B, the numbers are different. At 500 Kelvin, the value of Kc is 4.5 times 10 to the minus 2. And at 800 Kelvin, the value for Kc is 2.8 times 10 to the power of 3. Okay. One of these is an exothermic reaction, the other is an endothermic reaction. Okay. How would you deduce which is which? Okay, so you've got to remember that Kc is proportional to the concentration of products divided by the concentration of reactants. What we said was that if the value of Kc is greater than 1, then the reaction is going to lie on the product side. If the value of Kc is less than 1, it's going to rest more on the reactant side. So here we've got reaction A. So at the lower temperature of 500 Kelvin, it's got a value of 5000. At a higher temperature, Kc has decreased. Okay, so what that means is the value of the concentration of the reactants is much higher at the higher temperature, and the concentration of the products is much lower. If that is the case, then you can work out that the reaction has gone in the reverse direction. So it shifted at a high temperature, it's gone in the endothermic direction, and so therefore the forward direction for reaction A is an exothermic reaction. If we look at reaction B, 4.5 times 10 to the minus 2 at low temperature, at a high temperature 2.8 times 10 to the power of 3. Okay, so at the higher temperature we have got a high concentration of products, a much lower concentration of reactants, so we can then conclude that the forward reaction in this case is endothermic, okay, because Kc has increased and we've increased the concentration of our products quite well. Okay, now a couple more types of calculations. The first I've classed as easy, although it's not really that easy. So an example would be this. N2O4 and NO2 exist in equilibrium in a closed container with a volume of 2 decimeters cubed. At equilibrium, the amount of NO2 is 3.2 moles and N2O4 is 0.4 moles. Calculate Kc under these conditions. Okay. Now, the classic mistake students make is they go, NO2, that's the product, so 3.2 squared divided by 0.4. No, that's not right, because these are the amounts in moles. These are not the concentrations. So the first thing you have to do is convert to concentrations. And to do that, you divide your number of moles by your volume, which in this case is 2. So we've done it here. Moles divided by volume. So 0.4 divided by 2, 3.2 divided by 2. Okay, write your expression for Kc, and then you end up with a value which is 1.6 squared divided by 0.2, which gives you concentration of, which gives you equilibrium constant value of 12.8 moles per decimeter cubed in this case. Okay. If in work to 3 significant figures, unless the data in question specifies otherwise. Okay. So and a twist on this would be from the exam board. This one here, where you've got sulfur dioxide and oxygen making sulfur trioxide. And you've got a flask with a volume of 1.4 decimeters cubed. We reach equilibrium at a given temperature. The flask contains that number of moles of sulfur dioxide, that number of moles of sulfur trioxide. You've been given a value of Kc. So what you have to do then is to rearrange your equation to get the concentration of oxygen on its own, and then convert that concentration into a number of moles by eventually multiplying by the volume. Okay, so you can have a go at that one. The harder calculations are shown here, where you're given a starting number of moles of 1 or 2 or 3 reactants, or substances, should I say. It could be the reactants, it could be the products, and then you're told how much of one of these is present at equilibrium. Okay. What you then have to do to be successful and calculate a value for Kc is you need to be able to calculate the number of moles of the other substances at equilibrium, convert them into a concentration by dividing by a volume, and then solving it. Okay, so for example, question 1 here, it says A and B are in equilibrium with 2 moles of C. Okay. At the start of this equilibrium, at the start, you've got 1 mole of A and 1 mole of B, 0 moles of A. Okay. Now, what we've also been told is that at equilibrium, we have got 0.3 moles of A. So, the amount of moles that were reacted is the difference between 1 and 0.3. Or subtract 0.3 away from 1, which gives you a number of 0.7. Because A and B are you start with the same number of moles and they react in a 1-to-1 ratio, 0.7 moles of B will also have been reacted. So this means that at equilibrium you'll be left with 0.3 moles of B. Now, when it comes to C, it's slightly more difficult because you got a 1-to-2 ratio between A and C. So if you've reacted 0.7 moles of A, then you have formed 1.4 moles of C. And so that gives you that number of moles at equilibrium. So at equilibrium you'll have 0.3 moles of A, 0.3 moles of B, 1.4 moles of C. So that's another question here. Okay, you've got N plus 3P in equilibrium with Q and 2R. Okay, so we've been told here that we started off with 1 mole of N, 2 moles of P, and 0Q, 0R, but at equilibrium we were left with 1.2 moles of R. Right, so the first thing we can conclude is this, that if we made 1.2 moles, if we've got 1.2 moles at equilibrium of R, we made 1.2 moles. Now, because the ratio between nitrogen and R is a 2-to-1 ratio, then half as many moles of N were reacted. Okay. So half of 1.2 is 0.6. And so now we've got our basis of 0.6 moles, which means we can calculate the others. So the stoichiometry between N and Q is 1 to 1. So we've made 0.6 moles of Q, and between N and P there's a 1 to 3 ratio, so we reacted 1.8 moles of P. So the moles left at equilibrium is the difference between the initial moles and that which was reacted. So at equilibrium we'll have 0.4 moles of N, 0.2 moles of P, and we'll also have 0.6 moles of Q. Unfortunately, exam questions don't give you that much, don't give you that nice table, and so here we've got an exam question. We've got E plus 2F give an equilibrium of 2G. It says here a 2 mole sample of E was heated in sealed container with 1 mole sample of F. The equilibrium was established at a given temperature, and equilibrium form contained 0.8 moles of G. Calculate the amount in moles of E and of F in this equilibrium. Okay, so we started off with 0 moles of G, so we can work out that if 0.8 moles of G was formed, well, we've reacted half as many moles of E. So the amount of moles of E we have reacted is 0.4, and because we've got a 2 to 2 ratio between G and F, then the number of moles of F that reacted were 0.8. Okay, so that's our reacted moles, but at equilibrium we have got, for E, we started off with 2, minus the 0.4, we've got 1.6 moles present. For F, we started off with 1 mole, so 1 minus 0.8 equals 0.2 moles. Okay, and then the reaction, and then the question eventually goes on, gives you a volume, and then asks you to calculate a value of Kc. Okay, so very complicated. You need to have a go at these questions yourself. Okay, thank you for watching.